Hello, everyone. In this lesson, I wish to go over the intermediate value theorems again in comparison with the intermediate value theorem and its corollary. You know, when you work on this kind of questions, it really doesn't matter which one you quote, okay? Because either one works. The corollary is a special case of intermediate value theorem. In your proof, you must mention that the function is continuous on the closed interval. This must be mentioned, okay? And secondly, you need to demonstrate f of a and f of b are different values, and n is in between. In the case of corollary, and you demonstrated f of a and f of b, they're opposite in sign, and n is in between a positive number and a negative number. So it doesn't matter which one you quote, but you must make it clear that you have verified the conditions before you apply the conclusion. Okay, so I'm going to use the following example. I prepared some examples I'm going to show you. In the graph, as you have seen, that f of a and f of b are different in value, and capital N is one of the numbers between f of a and f of b. And you can also see that a, c, b, these values are on x-axis, they're input. F of a, capital N, f of b, they are outputs. And sometimes we may have more than one C's, okay, in this case. And but the theorem only guarantees there's one. Of course, if there's one, we can say there's at least one. Look at this first example. Okay, the first example, we want to prove that the intermediate value, we use intermediate value theorem or use a corollary, it doesn't matter which one you use, to show that there's a solution to the equation in the interval. And this part I wrote is as analysis. Analysis part is really something you will put on the scratch paper. You don't turn in. You don't need to turn in, okay? For example, in the analysis, right, how do we construct the function? Because in this intermediate value, in this question, we were not given the function. We have to figure out, right? So we say if this is true, right? If there is a solution to make it true, if this is true, this is to say that if there is a solution to make this statement true, right? So if this is true, then it will lead it with, add 2x, subtract 3 on both sides, and we will have 0. This is the clue. This is the clue as to the choice of function. Okay, the choice of function. And once we made the choice of function, we apply the theorem to the function. Okay, so then we can apply the theorem to the function. Let's look at the theorem one more time. So we want, right? we want that there's a function either equals to capital N, right, of our choice, which is going to be a constant, right? Or in the case of corollary, we want f of x equals to 0. Which one is easier? I think the corollary case is easier. But if you say, no, I'm going to choose a different function, and the way we do it I'm going to show you is not the only way. For example, you can write it this way, right? If this is true, right? If this is true, okay? If this is true, you could get e to the power x plus 2x. Make it equal to 3. Make it equal to 3, right? So you can make your capital N be 3. But then you have to construct an interval. You have to construct an interval that AB, so capital N is between f of A and f of B. I hope you understand what I meant here. Because capital N is between f of A and f of B, right? Is the given interval work for that? Okay, so I'm going to show you another way to do it. So you can see we're not stuck with only one way to do it. Okay, so first I'm going to show you if we choose 0, right? We choose a function. So this gives us a clue, right? So the first idea is that if we make a 0, then we get f of x equals to, and this is going to be our choice of function. Okay? And in the second case, I can choose the function to be f of x equals to e to the power x plus 2x, right? But this time, I'm going to have to use the intermediate value theorem. I cannot be using the corollary. All right? Okay, so let's see, we use the first way to do it. Well, in proof, okay, I'm going to remove these points thing, right? So that was not needed. Okay, so suppose at the beginning of the proof, because we are given the interval here, so we just need to show we must point it out that the function is continuous on this closed interval. Okay, you can say, oh, the function is closed on the entire number line. That's true, but you still have to mention that the function is continuous on the closed interval. Okay? The reason is that it is required by the theorem. In the theorem, it requires us to make sure the function is continuous on the closed interval 0, 1. But you can say, this is what you can say, right? On this side, you can say because f of x is the sum of exponential function and the polynomial, and the sum of these two functions is continuous, guaranteed by theorems, and it is continuous on the entire number line. If it is continuous on the entire number line, of course it is continuous on the closed interval. Okay, so you can say f of x is continuous on the entire number line. Is continuous on the entire number line, and of course it is continuous on this closed interval. You could say it that way, but it is sufficient just to say that. Okay, it is sufficient to say that. Number two, and we want to show that f of A and f of B are different. Okay, all right, because the theorem says so, right? The theorem requires so, and we need to demonstrate f of a and f of b are different. It doesn't matter which one you quote, right? So our interval has been set. So here we're going to say, okay, f of 0 equals to, you can come up with a number. Actually, you can actually find the number. But here we just estimate because this equals to 1. That's 0, right? So 1 minus 3 is negative. Yes, it is negative 2. It is negative 2 is less than 0. And e to the power, f of 1, e to the power 1 plus 2 times 1. And that's going to be e minus 3. I'm sorry, e minus 1, right? E minus 1. E minus 1 is positive. We have shown f of a and f of b are different. So you can mention f of 0 and f of 1 are different. They are different, not equal. Okay? So I'm using the intermediate value theorem. And one is negative, the other one is positive. Of course, they're different, right? Of course, they're different. Then by intermediate value theorem, between these two numbers, between negative 2 and positive e minus 1, there's a 0. So I basically have chosen capital N equals to 0. So this is my capital N. Okay, capital N is 0. And capital N is between, right? Is between f of 0 and f of 1. You can see that. If you insist to quote, intermediate value theorem. By intermediate value theorem, there exists a C. You must tell where, you must tell that there exists. You must tell the reader there exists. We are demonstrating there such number exists. We don't know what it is exactly, but we know it exists. And where is it? It is between 0 and 1. That's what the theorem guarantees. That's what the theorem guarantees. Okay? So that number that exists is such that the value of the function is equal to 0. Okay, equals to the capital N. And now, what does that imply? Since this is a guarantee to be true, then we just, adding 3 subtract 2c on both sides. So this is, and this statement now is guaranteed to be true because there's such a number c exists. And c now is the solution to that equation. You can see these two, they're similar, right? So C make it true. C make it true. So C is the solution to that equation. All right, so this is the first version. And the second version say, okay, I'm going to another way to do it, right? Another way to do it. We have decided that we're going to use this other function. We're going to use the other function. So in our proof, okay, so we're going to prove, in our proof, we're going to set another function. We let this function to be f. So we're going to apply intermediate value theorem to this function. So we let f of x equal to e to the power x plus 2x, right? Is this function continuous on 0, 1? Of course, it does, right? So we're going to bring the thing, what which is verified, right? It's continuous. It's the sum of exponential and polynomial. It's continuous. And next, we're going to demonstrate, but this is a different function, right? So we're going to demonstrate oops, sorry. I'm going to copy this function. I'm going to remove that picture. Okay, don't need to see that picture right now. Okay. So we're going to show, we haven't shown yet, we're going to show f of 0, right? And f of 0, that's going to be e to the power 0. 2 times 0, that equals to 1. And then I'm going to plug in f of 1. And e to the power 1, 2 to the power 1. And what do I get? I get e plus 2. E plus 2 is 3, right? So now we have demonstrated f of 0 is not equal to f of 1. Okay? And now we're going to apply intermediate value theorem. So I'm going to choose the capital N equals what? Between f of 0 and f of 1. So 3 is between f of 0 and f of 1. And f of 1. Right? Or some of you like, I know you probably learned it somewhere, that f of 0, right? So 1 is less than 3, and 3 is less than e plus 2. E is 2.7. So e plus 2 surely is larger than 3. So you can write it that way, f of 0. But it's at this time, if you'd like to write it that way, that's fine. Okay. So 3 is in between. So now we're going to apply intermediate value theorem, right? So I'm going to copy the whole table and put it right next to me. Okay, I'm going to put it right next to me. Okay, so what do I say? I'm going to just copy and paste the conclusion. I'm just going to copy and paste the conclusion. The conclusion is such, right? So, and I say by intermediate value theorem, right? There exists C between 0, 1, such that f of x equals to 3. Excuse me. Okay? C, sorry, f of C. So what does it mean f of C equals to 3? F of C equals to 3 basically is f of x, right? Replace f of x is f of C. So this will be replaced by C, and that's replaced by C equals to 3. All right? So we have proved with intermediate value theorem. Then you can also say that is e to the power C, right? E to the power C is equal to 3 minus 2C, which also says C is the solution, right? You can say i.e. C is a solution to e to the power x equals to 3 minus 2x. So there's more than one way to do it, but which way do you like? Which way do you like? Right? In this case, it doesn't make too much difference as long as you have all the points touched, right? So what are the points we need to touch? Number one, you need to visibly show the reader you have guaranteed the function is continuous on the closed interval, as is required by the theorem, Secondly, you demonstrate the number capital N you have chosen is between f of A and f of B. And C, you just apply the theorem. When you apply the theorem, you must use the same wording. You need to say there exists. This phrase is necessary. And the rest of it is mainly try to make it easier for reader to understand. Look, e to the power c is 3 minus 2c. That demonstrates that c is a solution to the equation. All right. On the first version, of course, you demonstrated they're not equal. Or you can say they multiply each other, it's negative, which also shows they are different. F of A and F of B are different. Okay, but in this case, you also have to mention explicitly to the reader that the function is continuous on the closed interval. Yes, it is trivial, but you must mention because it is called for by the theorem we are going to apply. All right. So these are the two different ways you can do that. Can you increase, invent other ways to do it? Of course. Okay. But making zero usually is a common practice. Okay. Making zero is usually a common practice. So, because it's easier. I think it's easier. Okay, you just move everything to one side and you create your function. But you don't have to. You can, do it the other way. Okay. So, in the end, how much do we need the graph? I would say you don't really need the graph. Okay, this is the graph I put for the function, for the first choice of the function. Okay, for the first way, right? For the first way, so your capital N between, right? This capital N, that's 0, right? On the other one, you can also do it, right? But you're going to plot this function, right? You're going to plot this function, and it's going to be 1 and e plus 2. So it's going to be in between. It's going to be in between. The curve is going to be slightly different because one has plus 3, one has subtract 3, and the other one does not have subtract 3. Okay, so I'm going to leave that for you if you like to graph it. Okay, but graphing is really not entirely necessary. So let's look at the second example. The second one, I'm going to remove the graph. Right? Remove the graph. In the second case, the analysis is similar. So what I'm going to do is that I'm still going to put the theorems right underneath. Right? I'm going to put the theorem underneath so we can use it, right? We can use it whichever way you use. But in this case, you have to create a function. We have to create a function. And also, we don't know what interval. Okay, real solution. Right? Sorry for the typo. So in this case, let's do the analysis part. Okay, analysis, analysis part. The analysis part is something I scratched out on my scratch paper. You don't need to show it. Wait, where did I put? Okay. Thank God I didn't delete it. I think I deleted it. Okay, never mind. We still have another one. Okay, so I put the theorem right next to us. Okay, in the analysis part, this part is like my scratch paper. This is my scratch paper, and I just first I need to identify the function. How do I identify the function? Well, if they ask us to prove there's at least one real solution, we can assume there is one. Okay, so that's why we say, well, if there is a solution, right? There's a solution to this equation. That means certain number make it true. Okay, so assume it is true. It's true for some x. Okay, if it is true for some x, right? So if this is true for some x, then I can subtract cosine x and make it equal to 0, because if this is true, then subtract x cubed subtract cosine x will be 0. So if this is true, then I can assume. So this is to give us the clue to identify the function for which we can apply the theorem or the corollary. All right. So this part of analysis is really to identify. So this is the clue. Okay. So this is the clue to identify the function. Okay. So we have identified the function. And what else do we need to identify? And it looks like we have a polynomial, we have a trig function, they're continuous on, so this function is continuous on the entire number line. And of course, it will be, continuous on any closed interval that we find, right? So we have identified that. Continuity is not a problem. But next, first we identify the function. So the first one, we have identified the function, right? We have one more step to do. We also need to identify the interval. Okay, we also need to identify the interval. How do we identify the interval? Right? And we know that this is going to be the capital N. This is going to be our capital N, right? This is going to be our capital N. So whether you say I'm quoting intermediate value theorem or corollary, it really doesn't matter. But we need to identify the interval. That interval contains 0 because N has to be in between, right? F of A, F of B must contain 0. So we're going to try to figure out what. So the easiest thing to do is to say, okay, one is positive, the other one is negative. So we're going to identify the interval. So what number? So this is the part you can play with it on your scratch paper. Okay, I'm still playing on my scratch paper. I would say, okay, so how about 0? I'm going to choose some easy numbers. 0, cosine 0. Well, 0 to the power 3 is 0 minus cosine 0. Cosine 0 is 1, so this is going to be negative 1. So this is negative, right? Next number I want to get, it could be any number I want, but I want it to be positive because 0 is between a negative number and a positive number. If I get another negative number, 0 is not going to be in it, right? So I'm going to try to get a positive number. But I also want to make it easier to calculate, right? Say, how about I choose pi, right? How about I choose pi? Cosine pi is -1, and pi to the power 3 is going to be, positive. And so this is going to be greater than 0. So 0 pi would be an interval, right? So we have identified 0 pi as an interval, right? One is positive, one is negative, one is positive. Is this the only interval? Of course not. Of course not. 2 pi will work, right? 2 pi will work. How about pi over 2? Hey, let's try pi over 2. Right? That's going to work too. And cosine pi over 2 is 0. Right? So this is 0 and this is a positive. So 0 pi over 2 will work too. We get more than one choices, don't we? So we can choose 0 pi, but now we have to make up our mind which one do we choose. And we have more choices, the 0, 2 pi. That would do too. So we actually have many intervals. So we're gonna decide which interval is going to be our choice. So you can see from this piece of work, which is the scratch paper work, but you should not turn in this scratch paper. And you should organize your work. You should organize your work. Okay, so now we can get started. Okay, now we can get started to show. Okay, so where do we start? We have identified the function. So we say, okay, let the function be such, right? Then I'm going to say this function is continuous. Continuous where? Well, continuous on a closed interval. You can choose any one of these. So I'm going to choose 0 to pi over 2. So can you say it's continuous on negative infinity to positive infinity? If you do that, you're going to lose some point because we do want the condition in the theorem to be matched explicitly. Then you say, yes, it is continuous on the entire number line, and of course it is continuous on the closed interval. But how about you pointed that out? We pointed out the most obvious to make our case. So this statement matches the condition in the theorem or the other one. We just want to see that. We just want to see that, okay? So show that. And next, we're going to show f of 0, right? F of pi over 2. Oops, I missed a 0, right? So the conditions are checked. F of A and F of B are not the same. Okay, and some of you like to say, that is, right, you want to explicitly to point out, actually you don't need to mention capital N equals to 0, right? You don't need to do that. You just want to point it out, F of A, F of B, they are opposite, as stated in the corollary, no problem. That's even better. Okay, this is a negative. And then what you say? You're going to say the same thing that we said earlier. Okay, so I'm going to do a little copy and paste to show you. Okay, you don't need to invent any language. Okay, but you should have these words in place, and every word is indispensable. Then you say, by intermediate value theorem, there exists C in that interval, but this interval is from 0 to pi over 2. It's a different interval, right? You pointed out the interval such that f of c equals to 0. So let's first do 0. F of c, right? What is f of c? This piece, right? And what is f of c? F of c, we're going to replace it by c. C. And that is, right? That is c to the power 3 equals to cosine c. And that means c is a solution to x raised to the power 3. So you see, there's a kind of rhythm. There's a kind of rhythm there. Okay, I wish you guys to see the rhythm and the common structure when we do this kind of work. And which part is your scratch paper work that should be left in the scratch paper, right? This part should be left in scratch paper. Your reader doesn't need to see it. Your reader just need to see this part of the work, this piece. That's all. You turn it in, you get all the points. You turn it in, you get all the points. And your reader sees clearly you have introduced a function explicitly, and you affirm that the continuity of the function on a closed interval, which is required by the application of this intermediate value theorem. And you also demonstrated that all the conditions are being satisfied by the intermediate value theorem or its corollary. And each word, okay, continuous on the closed interval, there exists a C, and this part of the structure, I don't think you should omit any one word. You should not omit any word. The rest of it is just a rhythm to show to the reader as clearly as possible that, sorry, this is C, right? As clearly as possible that we got a solution, and such solution exists. All right, so that was the second one. And in terms of picture, I did draw a picture. That's the picture. But you really don't need this picture. You really don't need this picture. Okay, so let's look at another one. I don't know how much time we have. I try not to make it too long. Okay, number 3 and number 4, I pick up a question from your homework to see one is a given interval and the other one is not a given interval. Okay, so one is a given interval and the other one is not a given interval. So by this time, in terms of analysis, we agree that making a 0 is easier, okay? So we say, okay, if this is true, right? If we have a solution, then we got a function, we got a sine x minus x squared. You can move things to the other side if you want to, plus x equals 0. So this is the clue, okay? This is the clue for f, for the function. All right? So our function is found. Our function is going to be sine x minus x squared plus x. Interval is given. Interval is given. Right? So in this case, we're going to start the work, proof. Okay? Remember, this is just scratch paper work. Don't need to show it. So we, at the proof, we say let, right? Let the function be such. Okay? And then we're going to point out that f is continuous. Well, this function is continuous on the entire number line, right? It is continuous on the closed interval. The closed interval, not the open. If you say it's open, then the intermediate value theorem does not apply. So you must say it's continuous on a closed interval, even though it was given as open. All right. Number two, we're going to check the value. So we're taking the second condition. Second condition. Okay, second condition. I'm going to bring the theorem with us one more time. Okay, for our convenience. Okay, we don't need to look at the scratch paper. So this function right there, and oops, the function will be evaluated as 1 and 2. So 1, 2, right? So 1, 1, 1, 2, 2, 2. Okay. When we evaluate f of 1, this is -1 plus 1. So this is just going to be sine of 1. Sine of 1 is positive. Okay. Because 1 as radian is in the first quadrant. You don't need to use a calculator. You don't need a calculator. Okay. The second quantity is that you can see -2 squared plus 2. That's going to be sine 2 minus 2. Sine 2 is going to be less than 1. So this is going to be less than 0. Less than 0. Do you need a calculator for it? No, you don't need a calculator. Okay? So all we have demonstrated is that 1 is a positive, 1 is a negative. If you want to quote, right? If you want to quote intermediate value theorem, and you can say let n to be 0, right? Capital N is 0. You have f of A is larger than 0, f of B is smaller than 0, n equals 0 is in between. Some of you like to explain, some of you like to do it this way, right? F of 2 is less than 0, and 0 is less than f of 1. If you insist to do this, I have no objection, okay? But it's not entirely necessary because it's pretty obvious. It's pretty obvious. And then we're going to apply, excuse me, we're going to apply the conclusion of that theorem, right? Once again, I'm going to do copy and paste. So you see, I'm just using the same structure of sentence, not wasting any words, not adding words, not removing any words, right? So, and of course, I have to change some parameters. By intermediate value theorem, there exists C, and C is between 1, 2, such that f of C equals 0. And of course, my f of C, now my f is this piece. It's a different function. So this is going to be C, C, C. That is, right? That is sine of C equals to C squared plus minus C. So C is a solution to the equation, which is right here. So I hope you have seen a rhythm at this point. You have seen a rhythm. You don't need to show the work, please, okay? Use your scratch paper as scratch paper, and you only show your best work, which is right here, okay? I'm double checking, okay? The next one, which is example number 4. It is pretty much the same question, but we pretend the interval is not given. Okay, interval is not given. So we can borrow the scratch paper work for the function, right? So our analysis is still here, but we have to identify the intervals, right? So if function is identified, right? Function is identified, but we need to identify, we need interval. Because we pretend that we don't know 1, 2. We pretend we don't know 1, 2. So we're going to identify interval. This time we try to identify a different interval because you can see the interval oftentimes is not unique. Sometimes if we're not given the interval, it's not the end of the world. We just identify them. Okay, we just identify them. So let's get started to identify the interval. Okay, so what interval I'm going to identify, right? I like to start with 0. Okay. Uh-oh, I got 0. That's not going to work. Why that's not going to work? Why is that not going to work? Because the next number is either positive or negative, right? The capital N cannot be 0, right? So we have to choose a number. If we want to use a corollary and we want to solve this equation, we cannot choose 0, even though 0 makes it so much easier. So how about I choose -1? -1, right? I'm going to choose -1, right? So over here is -1, and x is -1. Check if I identified it. I have plugged in properly. I have chosen x equals to -1. I chose x equals to -1. There's some sign of -1 is going to be negative, right? So this piece is going to be negative, right? So this is going to be negative because it's in the 4th quadrant, right? So that's a negative. But this is going to be +1, right? +1, so -1, right? So this is going to be -1, -1. So the whole thing actually is going to be negative, less than 0, according to my assessment, right? Because this is a -1 plus another -1, and that's going to be negative. And then what do we do? Right? We're going to try to get a positive number, right? We're going to try to get a positive number. So how do I get a positive number? Let's try to get a positive number. I'm thinking of trying pi, okay? So pi, I feel that's not going to work because sine pi is 0, right? And pi squared is larger than pi. So this is going to be negative. Oops, it's not going to work. It's not going to work. And then what do we do? We still have to keep trying, right? We still have to keep trying. How about we choose, they're both negative. That's not going to work, right? How about we choose a pi over 3, right? So we're going to choose a pi over 3. So this is going to be pi over 3, and this is going to be pi over 3, and that's going to be pi over 3. Let's see what we get. Okay? Sine of pi over 3 equals to root 3 over 2. Okay, root 3 over 2. And that piece, right? So this piece, what do we get? Between these two numbers, which one is larger? And I think, well, at this point, since we're doing so wildly, let's do a calculator. Positive. Yay, positive. Sometimes calculator is just amazing, right? Calculator is amazing. Oh, then I don't have to work on the pi. I don't have to change the pi because I have a positive here, I have a negative there. Boom. So between between f of pi over 3 and f of pi, there's a 0, right? So I got my interval, and that's my interval. My interval is pi over 3, comma, pi. You see, the intervals are not unique. And for the rest of the for the rest, I pretty much will copy this piece of work. Okay, to save time, right? To save time. And of course, I need to make some adjustment. right? I need to make some changes. I still use the same function. It is continuous on this closed interval, not a 1, 2 anymore, right? And f of pi over 3 is going to be positive, right? F of pi is negative, right? And in between, right, f of pi over 3 is positive. If you like, do that. And I really don't care that much about it because I feel it's not really necessary. Okay, so 0 in between. Do you need to mention capital N? You don't have to. It's optional. I can take it away. So by intermediate value theorem, there exists these C is inside this interval open, and C's f of C such that it is equals to f of C equals 0. You plug in, and boom, it's done, right? All that work you need to present is just this piece. All right. The graph, of course, is not entirely necessary at all. So don't worry too much about it. We're just working on applying the theorem. Okay. And you understand there are more than one solutions. And on this question, number 5, this is similar, but these functions, you know, for this kind of situation, we actually don't have, I think it is given like this. In this case, right, choice of function is very obvious, but we need to identify the interval. We need to identify the interval. And so the function, the choice of function is obvious, right? So we're gonna choose our function to be, oh, oops, sorry. That's our function. Okay, that's our function. Okay, so we can let this be our function. And of course, this is polynomial. It's continuous on the entire number line. So we just have to identify our interval, right? So we're going to identify our interval. The function is identified. So in the part we identify our interval, you should do this on your scratch paper, right? So analysis. So you can say, okay, I'm going to identify my number. I would start with 0. In this case, I'm going to start with 0 because it's just easier. Okay, it's easier. And so this is going to be equals to 1, and it's positive. And next, we need to choose, we're going to choose to say 2, right? If I choose 2, what happens? This is a -8, this is +8. We got a 1 again, so we get another positive number, which are the same. And this is not going to be useful because we want to make the equation equal to 0. So 2 is not a good number. So let's choose 3. Okay, so we're going to choose 3. When we choose 3, what do we get? This is a -27. This is going to be negative. Done. We have chosen the interval, and the rest is just applying the theorem, right? So our interval chosen is going to be 0, 3. And what if you want to choose, you know, -1? So yeah, there are many choices. There are many choices. So now we're going to say, okay, f is continuous, right? F is continuous on 0, 3. 0, 3. And f of 0 is positive, right? F of 3 is negative. Yes. And if you like to say f of this is true, no problem. No problem. Right? So you use the corollary. Okay, so then you say applying apply intermediate value theorem, right? By the intermediate value theorem, right? There exists a C, or there exists such, well, capital N is 0, right? So there exists C, and where is C? From 0 to 3 in that open interval such that f of C equals to 0. I'm sorry, I forgot this C, right? F of C is 0. And what does that mean? That means that this one has a solution. Okay, which is that, right? F of C equals to 0, right? That's what we want to prove. That's it, right? You can, if you like to be more elegant, you can say i.e., that the equation has at least one solution, as is stated in the question itself. Okay, there's no necessity to draw the picture, but if you draw the picture, okay, actually I drew the picture to share with you. Okay, you may identify different intervals, right? -3, +3 will work, but there are more than one solutions. You can see. So this theorem, right? You can, there's another version, right? There are more than one solution. If you draw the picture, right? If you draw the picture, there's another one, right? If you draw the picture, you might identify intervals and may contain more than one solutions. Okay. So I'm going to put this theorem here. And so another version of proof. Okay, another version of proof. That's the change of interval. Just change of interval, okay? But in this case, you can see I chose a different interval because I saw the picture. I had a peak, right? So -3, so f of -3, right? Greater than 0, f of 3 is, wait, f of 3, wait, is negative. Is that right? Yeah, it's correct. I just didn't calculate. So f of -3 to f of 3, the product is less than 0. The narrative is still the same. Okay, there's at least one solution. So the choices of intervals are often not unique. So if you have a peek of the picture, certainly it helps. Right? Last but not least, I think I'm just going to quickly finish this one because so the proof is here. Just the next one is similar, right? And I'm going to quickly put the solution out there. Okay. So this question is also that this is equal to 0, has at least one solution. So we're going to have f of x equals to that piece, because in this case, it's just so obvious. It is continuous. We identify the interval and f of -3. And I have done the calculation. I've done my homework. So this is the picture, right? This is the picture. And I just need to put it in place. Okay. I found these examples. If you want to practice with these, okay, so this is less than 0. This is greater than 0. The interval is still -3 to 3. What a coincidence. But I think you got the hang of it, right? So f of c, this is our f of c, right? F of c, this is going to be c, right? And so in the end, this has a solution. It has at least one solution. And let me quickly scan this, right? So we got solutions. So to summarize, right, so this is the picture of the function. This is the picture of this function. Okay, so if you can draw the picture, it certainly helps you to identify the interval. I think that's all. I think that's all. To summarize, right? What is the format, right? As you often ask, how do you show work? When you show work, follow these examples. As you can see, the proof part we show, the proof part is what we want to see. All the other things need to be cleaned up, If you need to do some preparation to identify the function, identify the interval, those works should be put on scratch paper. Okay, so this is the best work I mean. Okay, this is the kind of best work I mean. The picture, not really necessary. Okay, so when people read your work, people can clearly see you're checking the conditions of the statement in the theorem for the premises. Each premise is checked and verified, identified correctly. And then you apply the theorem. And when you apply the theorem, you pretty much copy the structure sentence and the words, right? There exists. You must use the word there exists. You can't just write a C without saying, what is this C, right? You need to tell this where C is and what C will cost, right? The consequence of having C is to make the statement of the equation to be true. All right. Thank you for watching.